started here. For those of you who haven't gotten your test, please come up here and get your test. They're in alphabetical order and 5 groups in this breakdown of the letters up there. And let's talk about the test, go over the test. I've got some other things to send around while you're here. Here is, well, just a big packet of homework that hasn't been picked up in one time or another. And here's some more, chapters 4, chapters 5, and a bunch of other things to pass back. But I'd like to take a moment to take a look at the test. Here's the breakdown. Huge range in scores as typical on the second exam. Average score of 68, again, typical of the second exam. I don't need to tell you, but you took a hard test on Wednesday and you probably realized that when you sat down and started working on the problem. So it is some tougher material, tougher decisions to be made, harder decisions to be made, and it's just the nature of the material. You have to decide, do you do it by forces or do you do it by energy? As far as calculating your grade, remember this. This is how your grade will eventually be calculated. If you remember from the very beginning, come on by here, that the tests in this class will count as 75% of your grade. And so you have 3 in-class tests, counts as 50% of your grade, 1 final exam, which counts as 25% of your grade, and then you've got labs at 15% of your grade and homeworks at 10% of your grade. And so just to remind you, particularly after the second test, because I think after this test, everybody needs a little word of encouragement. It's like, ooh, you may have seen a difference between the first one and the second one. Although I did scan, there were a number of people who did better on the second one than the first one. And so, if that was you, more power to you. But if you scored in the, particularly in the 80s or 90s, but even in the high 70s or mid 70s on this one, you did a good job. It was a hard test here, and like I said, that's the nature of it. But do yourself a quick favor, do a quick calculation, and remember to factor in all the features, not just this test. Because this test, like I said, it may not be as high as you would had hoped. Hopefully it is. And like I said, some of you it's higher in this one than the last time. But for most of you, that's not the case. And so you might want to look at that. Take your first test, take your second, average them together, and you can see where you are now. This is your average as of now. And so I would put those average in right here and say, okay, that's where I stand. And then you can kind of look. Maybe you're getting an average of, say, let's say 75%. If you are, then you put in your average of your 75% here at 75 points. I'm going to trust that you still did all your homework and all your labs, as most of you, if not all of you, have and are doing. And so if you do that, that really helps with the grade. And here's how it kind of breaks down. If you kind of go through here and put in 86% and all your homework's in the lab, this comes out to be 90%. So if your average on your 2 tests is above 86%, good, very good for you, because you're clearly at an A level. The B level, it means you got to get a 73% or higher there, and that's what the number I was just quoting to. And then to be above the C level, you got to keep it above 47% on average. And like I said, I think that's more than fair in the sense that you really have to, not do the homeworks in the labs and not study, I think, to get to less than a C, because your tests can get pretty low, and as long as you keep trying and keep doing that, that really brings up your point scale there. Okay, and so there's the like I said, the breakdown of points. Well, I thought we would look at this and see where you did or didn't go wrong. I know there's always some questions at the end of the second one, more so than the first one, about, wait a minute, what did I do wrong? Particularly number 4. Number 4 got some little subtleties in it. Now, I don't want to start on number 4. Don't get me wrong. We'll start at number 1 and go all the way through. But number 4 can have some little subtleties, and I think that threw a number of people off there a little bit. And but even the other ones can get kind of tricky here. So let's take a moment to go through. Take this as a learning opportunity. If you did well, great. If you didn't do so well, let's learn it now, because I am going to give you another opportunity if anybody wants. Here is an extra credit problem. So I'll pass it around. You can grab it if you want, put it in your little notebook, and you can finish it up. I'll give you 1 week to do it, so you're not rushed between now and Wednesday. It's not any longer than any other problem. It's just a 6th one that I was thinking about putting on the test. Chose not to put it on the test. What is it worth? Well, it's worth 30% of the points you missed. I'll let you do the math on that. It's obviously going to vary from individual to individual, but it's worth 30% of the points that you missed. So if you did really, really low on this, this is a lifesaver. If you did kind of in the average range, which most of you obviously did, you know, it's going to tack on a few more points and, you know, give you something to hold on to and go a little bit further. If you did exceptionally well, if you were one of the few who got 100%. You can choose to do it anyways. You'll probably ace it off in a couple of minutes anyways here. So there's the extra credit problem here. All right, let's look at this. Let's see if I can clarify any questions or difficulties. I will say this in general. I said it at the beginning, and it's just worth saying again and again and again and again. Do the free body diagram. I mean, if I could say anything, looking back, particularly number 1 and number 3 here, I really got the impression that those who were missing it and missing the idea, it's because you weren't drawing the free body diagram here. Number 4 I guess I'll get to when I get to it. But I'll start right here. Number 1 is a pretty complex, test way over there, a complex looking problem. But I tried to give you a hint here, and the hint was you only need to look at the free body diagram for the top block. And once you get it for the top block, you'll see that that's enough information to solve the problem here, even though you're not even pulling on the top block. You're pulling on the bottom block. But the question is about the tension. So I'll start number 1 this way and say, okay, here's number 1. What is the free body diagram here? And so number 1 looks something like this. It's got this block, which we are told is 10 kilograms. And it is sitting on top of another block. And let me not draw too much of that block, because that kind of defeats the purpose of the free body diagram here. But in order to do a free body diagram, we want just the object and then the forces on that object. And clearly one of those forces must have been T, the tension. That's the problem. Find the tension in that cord. And so it's being pulled at some angle of 40 degrees. So clearly that's touching it. So hopefully you had that right away in your free body diagram. The other thing in your free body diagram should have been this, that this bottom block, you test over there on the end. You can get your forces by saying, look, the bottom block is obviously touching it. And so there would be an upward force of N. And maybe the trickier one of this is there any friction here? Yeah, in what direction? Yeah, and so it is in that direction. It's the bottom block here that is being pulled out. And so if I was doing a free body diagram for the bottom block, there would be the force of friction on the bottom block. The bottom block has some friction opposing it. The top block is then being pulled forward. In fact, you could even imagine if the string wasn't here and you cut it and you pulled it, the top block would come forward. That's because that's where that friction would be. So that was a big step here. What direction is that frictional force there? And it comes back to what I was saying, and in fact I'll probably end up saying this through all these problems, is do you got a good physical picture of what's going on? It will help you as you do the free body diagram and as you try to set up your equations. And why are they the way they are comes back to that picture. Well, the other force that is missing from here is then the weight of the block. So we've got the cord or the cable touching it, and then we've got the bottom block pushing up on it with some friction and then gravitational. And so there's the free body diagram. So hopefully you did that somewhere along the line then, and then you went ahead and did the sum of your forces. So the sum of the forces in the x direction, hopefully you set equal to 0. And likewise for the y direction, because that's the idea. The bottom block is being pulled out, but the cable there in the top block is holding it into place. No acceleration for that top block, either in the x direction or the y direction. So then, as we work this out, we can look at the x direction, and what you'll see is there is the force of friction pulling to the right here, and if we use the traditional coordinate system, that is a positive force. There is then a component to the tension, and so cosine of 40 degrees would be the component that way. And so there would be my first equation. And then the second equation would be the stuff pulling up, which would be the normal force, and it would also be T sine 40 degrees is pulling up, hopefully equals, or excuse me, and then the stuff pulling down, which is gravity, and then all that equals to 0. So there's my two equations. I'll do the y dimension first. So the y dimension says mg minus t sine of 40 degrees is the normal force. And now if you take that and put it up to here, what we have is the force of friction equals to tension cosine of 40 degrees. Force of friction is coefficient of kinetic friction times the normal. And so now I've got coefficient of kinetic friction. I've got mg minus t sine of 40 degrees equals t of cosine of 40 degrees. And so you can see some like terms here. And as we multiply this out, we get mu k mg minus mu k t sine of 40 degrees equals t cosine of 40 degrees. And so if we put all the stuff with t in it on the same side of the equation here, and I'm just going to put sine of 40 degrees and factor out a t just because they're in each one, and then I'd get a mu k mg. And so once we put in our numbers here, our tension comes out to be about 53.8 newtons. So there's number one, okay? Free body diagram, add up the forces. Hopefully it looks just like we did in chapter 5, Newton's second law, okay? Add up those four forces. Being careful to make sure you take your x components and your y components and put them together. 2 turned out to be a little challenging problem for a number of you, and I can see why. We got kind of a lot going on here. We got two objects. We got a spring. We got gravitational potential. We've got friction. We've got all the pieces. I don't know if you looked. Probably not. You probably had enough time just doing the homework. But this was one right out of the book there, and it was one of the ones real close to your homework, and if you look there, you'll see the problem. But basically, it's something like this. I'll kind of draw the picture again there. I know you have it in front of you, but it has this one block going up around a pulley, and then coming down on this sphere, and then this spring. And so we pull the block down. Let's see, we pull this block one here, so this 20 kilogram one, and the sphere is 30 kilograms. But we pull this down to this point right here, which they said is 0.2 or 20 centimeters here. So we pull it down 20 centimeters and we release it, watching it go back into, back to this spot. And then the question is, what is the speed of the 30 kilogram object as it returns to its unstretched position. Well, hopefully the decision you made right here is one on energy, and most of you did, but for those of you who didn't, remember, when do you make a decision on energy? When you've got distance involved here, right? It will really help when you get into step 5, where step 5, I left it as you could go either way on number 5, but I think number 5 is a lot easier with energy than it is with forces, although it's not too bad with forces, but you have distance involved. This one is tons easier with energy than it is with forces, because that spring has a force that varies with distance and gets pretty complicated, and we would want to know it in terms of distance, not in terms of time, which would be acceleration. Well, the idea here is that hopefully you said the initial potential energy, and I'll put it in two pieces. There should be a spring and a gravitational, and then the initial kinetic must equal then the final spring and the final gravitational and the final kinetic, and then any heat that might have been created along in the process. And so there's hopefully step 1, throwing out conservation of energy. And so now we can begin to analyze this. Now, it depends on what you call as your 0 point. And I think it would make most sense to say, well, for this block, I will call this point my y equals to 0. And then for this block, why don't I call down here before I stretched it? So imagine it was down here. Then this would have stretched 0.2. So as I pull this down 0.2, this stretches up 0.2. But why don't I call that y equals to 0 for that block there? That way, when I come over here and I say, all right, what is my initial spring's energy? It has this spring that is stretched a little bit, and the distance it is stretched is 0.2. So there's kind of my first step. In fact, I'll go down to the next line, because this one needs a little care in watching your units. I think you noticed already, didn't I convert centimeters into meters? So this is going to take us all the way back to chapter 1. Watch your units. So if you were one of those who didn't change your centimeters into meters, be careful, because now you're not matching the units here, which are probably joules, or I say here, which is probably joules with this one. You got to match joules with joules with joules. So if you're going to use these other ones in joules, you got to make sure this one is in joules. So you saw that a couple times on the homework and the examples I was doing, and same thing here. Make sure you get this in meters so it can come out to joules. And the same thing can be said about K. If you'll notice, it said K was 2.5 newtons per centimeter. So again, it's not in the units, it's going to come out to be joules here. So why don't I replace that with 2.5 newtons? And remember what a centa is. Centa means 100th. And so again, just get rid of the prefixes there. And so I'll put in my centa. And so that makes my 250 newtons per meter. So this is 250 newtons per meter here, times a distance of 0.2 squared. So there's a little subtlety in there that caught a few of you off guard there. Watch your units, watch your centimeters, watch your, well, and I guess it's centimeters also for K. Now, going on forward here, looking at the initial gravitational potential energy, if I had pulled it down to here and I called this y equals to 0, then this one doesn't have any gravitational potential energy, but this one does. This one I've got up here, and it's at a height of 0.2. So this would be my 30 kilograms times my 9.8 times my height of 0.2 again. And so again, to make it come out to be joules, make sure your centimeters is in meters. And so that would be my first approach. I'll put a 0 here for completeness. They do say you hold it in that position and you release it from rest. Okay. So you you pull it on down, you're holding it there, and you release it. All right, so there's my left-hand side of the equation. The right-hand side of the equation, then, okay, as it returns back. So this begins to come down. And this comes down for really two reasons. I mean, number one, it just weighs more than that one. And this one's even on an incline, so that alone it would come down. But in addition, it comes down because the spring's pulling on it too. So for two reasons, it comes down. One because of the spring's energy, and one because of the gravitational potential energy. But then as we get to this other side, we could say, well, the final spring's energy, well, that's the question when it gets back to equilibrium. Okay, so there's no x. And then we have the gravitational potential energy. So this one came back down to 0, but now this one went uphill. So I would have a little bit of a gain in energy of that one. So this one's going to go up. And so this would be a 20 times a 9.8. And then how high did it go? Well, I guess it's 0.2 times the sine of, and this little incline is 40 degrees. So sine of 40 degrees is how high up it goes there. So that's the gravitational potential energy. And so then as it comes back, you can kind of see, and again, this is where a good mental picture helps here. If you don't see the physics of it, you don't end up writing out the equations correctly. And of course, if you don't write out the equations correctly, you don't solve it. But for those of you who may not have seen it, it's kind of doing this, right? It's going like that. So when it gets back to equilibrium, aren't both objects moving? And so make sure you include the kinetic energy of both objects. So there would be a 1/2 a 20 v squared and a 1/2 30 v squared. And fortunately for us, the v's are the same. I know we did a bunch in class with pulleys, and we talked about this a lot. Sometimes the v is the same. Sometimes they are different, depending if it is one of these movable pulley things. And we have to be more careful. But we don't have that. We have a simple pulley system. Now that'll change when we get to step 5. Then we have a movable pulley one. But this one, they're each moving at the same speed. So you can see that we know that numbers, we know those numbers, we know those numbers, we know everything here but v. And so it's going to take a little bit of calculator work, but once we do, we get a speed of about a 1. And so this is the speed when it gets back there. So again, it's a conservation of energy. So one with Newton's laws, the other one with energy. Obviously those were the two big themes, chapters 5 and 6, and then chapters 7 and 8. So there's our chapter 5, and there's our chapter 8, if you will. Now we'll go back to forces. Look at number 3. Number 3 is a problem that looks something like this. It's got a pole that's spinning, and there's this little mass, and as it goes around and spins, it makes a radius of 15 centimeters, if I'm not mistaken. Yeah, 15 centimeters. Again, converting that over to meters right away here, otherwise I might get myself into troubles here. But there's my 0.15 meters, or just need to pay attention to what my units are. The angles are slightly different. Let's see, this is 50 degrees here, this is 60 degrees here, and this is 200 grams, which again is 0.2 kilograms. But it's spinning in a circle, and the question asks for attention. Hopefully, chapter 6 goes off in your head right away. Yeah. Oh, back here? Yeah.
The heat on that one.
Oh, shoot. I forgot to write down heat. I guess I should look at my answer sheet. Thank you. There is heat on that one.
I'm sorry, I got some extra credit on that one since we forgot to.
Fortunately, I didn't forget it when I was grading it. I was trying to go quick, save some time, but I shouldn't have. Let me read the problem again. 20 gram, 30 gram, yeah, coefficient of kinetic friction. So, yes, there is some heat here. Okay, so I'm missing a piece to this puzzle, and that is this one, which is the kinetic friction times the distance traveled. And so now we've got to do a little work here. This is the coefficient of friction times the normal times distance traveled. And probably doing a free body diagram over here is important here, although we've done this one quite a bit. So hopefully you haven't forgotten here, but this piece right here would be the sum of the forces in the y direction if we put a coordinate system here that is y perpendicular to the incline and x up the incline. And so then we would have a normal force going up and an mg cosine of 40 degrees going into the board. That must equal to 0. So the normal force is mg cosine of 40 degrees. So one of those standard incline ones I know we did a lot in class, but a little bit harder than just the normal force is mg. So it's normal force doesn't equal mg, but it is mg cosine of 40 degrees. And then the distance it traveled is the 0.2. So as I put in all these numbers, coefficient is 0.45, mass is 20, let's see, mass is 20, g is 9.8, cosine of 40 degrees, and distance is 0.2. Ding, 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 ding. Yeah, okay. Yeah, and without that, you wouldn't get a 1. So you need that. So between this number, let's see, I got that number, good. And that number, good. And then the 2 kinetics, good. And then the 1 gravitational, good. And then the 1 heat, good. And then when you do all your math, you come out to a speed of 1. So yes, you'll need that for that to work out. So, yeah. All right, so hopefully that made sense. Now back to number 3 here. Number 3, it's spinning around. Hopefully the first thing you did was draw a free body diagram. And if I do that, let's see, I've got tension number 1 at some angle of 60 degrees. Tension number 2 at some angle here from the vertical at 50 degrees. And the one I'm missing here, or the force that needs to be on here that maybe isn't so obvious, but is mg here. So don't forget that in your free body diagram. So we've got our 3 forces, the 2 tensions and then the gravitational force. So as I said before, always look for the things that are touching it. You'll get a force from everything that's touching it. So in this case, the 2 strings, string 1, string 2. And then of course the non-contact, the field force is in there in terms of mg. Now we need a coordinate system. And I suppose I'll just stick to the traditional coordinate system, xy here. But if you do that, you can look at the sum of the forces in the x direction and the sum of the forces in the y direction. And it's the x direction that is the most crucial. This is why this was in chapter 6, is as it is going around, particularly when it's right here, the center of the circle is over here where the pole is. So as this thing is spinning around, we want all these forces to come out to be a negative direction. So there's the center of the circle towards the negative direction. And we want it to come out to be an mv squared over r. Not 0 this time, because this time it is accelerating. And so that would be the forces in the x direction. Now in the y direction, we want that to be 0. We don't want it accelerating in the y direction here. And so that's a big key to the problem. That's what chapter 6 is. And so we can add those together here. So now as we begin to do that, let's see what we have here. This one has a T1, yeah, it depends which angle you want to use, but I'll use the 60. Okay, so I do want sine. So I will go sine of 60, and that's pushing in the negative direction. And also T2 sine of 50 degrees. And so there's my physical picture, that what I have is both of these are pushing inward. And so both of these are pushing in the negative direction, or they have components. So magnitude, component, direction we talked about. Magnitude, component, direction. So I put those two together, that has to come out to be mv squared over r. And then also in the vertical direction. In the vertical direction, I've got T1 cosine of 60 degrees. So this one is lifting up, and these two are pushing down. So this is T2 cosine of 50 degrees and minus mg. But there's your standard two equations, two unknowns. Now I say two unknowns because you are given the mass. Okay, so there's the mass. Don't forget to convert it to kilograms. So there's a 0.2. You also know G as 9.8. You also know, well, here's mass again, so there's the 0.2. There's the R I was talking about, and since we're going to use G in terms of meters per second squared, make sure you do everything in meters. So that's why I'm going to convert my centimeters into meters. And then probably the next difficult step here is velocity. What is the velocity of this thing that goes around? Because the problem doesn't say, it just says that it makes 300 revolutions in 1 minute. And for me, I like to do it this way and just say, all right, that would be 2 pi r. That's 1 revolution distance, right? That's the circumference. So then they're saying I do 300 of those in 1 minute. And so there's my equation for velocity. The distance traveled, time taken. And so remembering that this is 0.15, then gives me a velocity of 4.71 meters per second. And if I could say there was any common error, it was the fact that many people broke this down to the number of revolutions per second. They took the 300, they divided by 60, and they got like 5 revolutions in 1 second. And then that's not wrong, it's just not complete. That's how many revolutions it does. That's not its velocity. Velocity is the distance it travels. So we need to get its distance. So you still need to do, 5 revolutions in 1 second to figure out what its linear speed is. So we need distance, not revolutions. Okay, so once we know its speed, we can put that into here. And so this first equation now looks something like this. It's a 0.2 for the mass. It's a speed of 4.71 squared for the velocity. It's a radius of 0.15. I'll even go ahead and drop off the negative because it shows up in every term. Then I have the sine of 60 degrees T1. And then I have the sine of 50 degrees T2. And so I know those. The second equation, and I'll move this so it's a positive, becomes a 0.2 times a 9.8. So that's what would happen when I move this over to here. And then it would be cosine of 60 degrees T1, and then minus a cosine of 50 degrees T2. But what I do want you to see then is I've got the standard 2 equations, 2 unknowns, and now you can solve it with whichever method you enjoy the most. It looked like most of you did a substitution. That's fine. Although for me, this one's kind of long with substitution. I would prefer either an elimination, which would make more sense, or actually a little bit of Kramer's rule in our matrices is personally what I did, although I didn't even work out the Kramer's rule. I just punched in the matrix into the calculator. I'm glad they have these calculators these days. And so anyways, just put in the 2x3 matrix and came up with the Kramer's rule. But whatever method you want, and like I said, probably for most of you it made sense to solve this for T1 and substitute into here, and you get it. But if you did and you went through all this math, you've got T1 is equal to a 21.85 newtons, and T2 a 13.94 newtons. And so there's our two tensions as it spins around here. And again, not to belittle the math, but that's not usually where the challenge is. The challenge is usually back here in the physics, is, you know, writing out all the forces. Maybe it's drawing the free body diagram. Maybe it's realizing it's accelerating because it is going in a circle. Although I didn't notice that mistake. That's a very classic mistake that I don't think anybody made. I don't recall anybody making it, but just forgetting that it accelerates, you know, and you don't set it equal to mv squared over r. You just set it equal to 0. But it is accelerating because it's changing directions. You know, it's not accelerating in the sense that it's going faster or slower, but it is accelerating because it's changing directions. Well, then on to number 4, which, of course, just by the nature that it's number 4, is probably telling you it's going to be a hard one. 4 and 5 are always those hard ones there at the end. It's got 2 parts. I think that makes it harder. But there are also 2 parts that you already solved. So I was personally kind of curious on this. I was like, okay, we'll see what happens. Are they going to ace this one? Or are they going to treat it like one they haven't seen before? And probably most of you treated it like one you hadn't seen before here. So obviously it was hard for a number of you. So let's go through this. But this one about the first part, what is its maximum displacement? I can't remember. Did we do that in class, or was that on the review test? Does anybody remember that one? The review, yeah. That's what I was thinking too. I don't recall setting this one up in class here. But let's do A here together. At first, here is this idea that we start up here, and we've got this spring down here, and it's going to drop down. And again, watch your units again. I know it says 135 centimeters, which is 1.35 meters, okay? So make sure you convert it. Don't leave it in centimeters, okay? Watch those units. Okay. How about K? Is K in centimeters? Okay, K's not, so that's nice. They just give us K straight up, 35 newtons per meter. They do give us the mass, though, at 450 grams, so make sure you don't get trapped in your units there, and you go, okay, kilograms, and so that's 0.45 kilograms. But here's the idea, and this is a big one where you got to kind of see this physical picture, or you're going to miss something here. But it starts up and it goes down the hill, and it goes faster and faster and faster. Now this one does have some friction, so we're going to have to take into some heat along the way. And then it hits the spring and it compresses the spring. But don't forget this part. As the spring is being compressed, isn't there still friction? Yeah, so don't forget friction as that spring is being compressed. And so there were a few of you who did the friction great up to the spring and then treated the rest of it as it was frictionless. And I wasn't sure if you thought there was no friction there, or it was just an oversight and you weren't reading the math and saying, oh, well, just put in 1/2 kx squared and forget the frictional part here. So that was probably the most common mistake, is as that spring is being compressed, there still is friction. And likewise, as the spring is being compressed, isn't there still gravity? So isn't there lowering of gravitational potential energy as the spring is compressed? And so maybe that was probably the second mistake, where again, a number of you just calculated how fast is it going here, and then you treated it as if it just hit a spring. That was it. No gravity, no friction. And you forgot that those other 2 parts. There's still friction and there's still gravity. So here's the idea. First of all, I would call y equals to 0 at its lowest point, and most of you did. You said, okay, let's say it compresses up to there. All right, so let's call that y equals to 0. And what it did is, let's say it compressed the spring a distance of x. That's been the variable we were using. Because if you do that and apply your energy here, you will have then your initial gravitational potential energy. And there is no initial spring and no initial kinetic. And so you'll have this first one as mgy initial. M being the 0.45 kilograms, G being 9.8, and then your height then is made up this little triangle right there. This slope is a 40 degrees. So what I would have is 1.35 plus x sine of 40 degrees. And so this is the part that I was commenting about. Don't forget the plus x. Don't forget that as the block is hitting the spring and bringing it down, that there was energy associated with that. Now don't get me wrong, you could have put y equal to 0 here, and that's fine. It's just now this plus x would be gone on this side of the equation, but then the x sine 40 better show up on the other side of the equation, you know, because it doesn't finish at y equals to 0. I think it's best to always put a beginning or an ending point of y equal to 0, but you don't have to. You could have put right at the spring, but somewhere there needs to be that x, whether it be on this side of the equation or the other side of the equation. So that's your initial energy. And so what happens is it goes down this incline, and as it goes down that incline, where does that energy go? Well, as I said, it compresses the spring, so there would be our 1/2 kx squared there. That's where some of it went. And as I said, it gets down to here, the gravitational potential energy is 0. But then there would be heat energy down here. And so there is our Q that we've been talking about as it went down. The same as problem number 2 that I overlooked. And so here is a 1/2 kx squared. Then this would be the coefficient of the kinetic friction times the normal force, which is mg cosine 40 degrees. So again, it's just like the number 2. There's the normal force. And then times the distance traveled. 1.35 plus x. Don't forget the plus x. And it was obvious that that was the number 1 problem right there. Just people forgetting that, hey, as this spring is compressing, that's part of the distance it traveled. So part of the distance it traveled going down, so include that part of the potential energy, and also part of the distance in terms of the spring. Then other than that, it's throw in the numbers and then solve for it. It does turn out to be a quadratic equation. There's the quadratic part of it. These numbers are all given here. The coefficient of friction was a 0.25. The mass is the 0.45. G is 9.8. Cosine of 40 degrees, 1.35 plus x. And this side of the equation we already mentioned. So half of 35 is 17.5. That's the only quadratic term. But there is a linear term here. There is all of this times an x. And then there's this side of the equation, all of this and an x. So if I put them together on this side of the equation, it becomes a negative 1.99x when I put my linear terms together. And then likewise, I have this term, which is a constant, and I have this term, which is a constant. And if I put those together, I end up with a negative 269. And so there's your mathematical equation. So again, maybe I'm wrong here, but I don't think it's the math that is the challenge. Maybe it is, because again, I don't want to belittle the math here, but it's really writing it out correctly. That's that first key step. Starting with that basic fundamental principle and then applying conservation of energy. And it's this extra 1.35 plus x and the 1.35 plus x. So plus x for the heat, plus x for the potential energy. Because once you've done that, then the x comes out to be about 45 centimeters, 0.45 meters. And so there's the practice test problem that I think you guys saw as you were preparing for the test. And then the second part of this was the part you saw me do in class with the cannonball. It was, okay, where along its motion then is its maximum speed? Yeah, and this one really comes down to that point. You got a good physical picture of what's going on here. Because it is so tempting and so wrong to say that the maximum speed is right here when it touches the spring. I mean, I know why you're first thinking. You're first thinking, well, as it goes down the hill, it goes faster and faster and faster and faster and faster. And then it hits the spring. And then what happens? It doesn't slow down yet. It still goes faster and faster. Why? When would it start to slow down?
Acceleration.
Yeah, and so maybe a free body diagram is worth drawing right here. As it's coming down the hill, we've got gravity pulling it down the hill, mg sine theta. We've got friction pushing it up the hill, which would be our coefficient of friction times our normal. And so that's before it hits the spring. Now obviously then, this number must be greater than that number, which is the whole reason it goes faster and faster and faster. But when it hits the spring, what happens? Well, I guess then there would be an additional force from Hooke's law, kx. And how much force you get from that spring depends on how much you've compressed the spring, right? And so this is really the key to the problem. When you first touch the spring, x is 0. You haven't really changed anything. You still have a greater gravitational force than friction. Now, as you start to compress the spring, this number gets bigger and bigger and bigger. But for a while, these two together are still smaller than that one. And so what happens? It still keeps going faster. And so you don't get the maximum speed. So many of you will see there on the paper, you know, I say, not at spring, you know, and so it's like that's just not it. You got the conceptual wrong, and I gave you a few points for it. I go, well, all right, I got to give, I'll give you 3 out of the 10 for that. Why not? And so a lot of you see you got a 13 because you did part A completely right. And then you go, oh, well, then this is the thing. And so, you know, it's a 13. I was like, oh, man, you missed that physical picture. And now the problem gets kind of hard, you can see. The problem gets like, okay, where is this? So the key is to realize that it's going to compress the spring. Now, it turns out not to be very far, but I think it's 5 centimeters or close to 6 centimeters. We'll do the math here in just a second. But it's going to compress it, and this force needs to build up before these two are equal to that one. And then, of course, after that, then these forces are greater than this one, and then that's why it comes to a stop eventually. And looks like it takes another 40 centimeters before it stops. But I think it comes out to be about 5 centimeters. I'll look at the number here in just a second. But that's the key. When does mu k mg cosine theta, that's the frictional force, and the force from the spring, when does it equal the gravitational force pulling it down the hill. So if you set those two equal, we're looking at 0.057 meters. So close to 6 centimeters. So it's not right at the spring. It's 6 centimeters further. And I don't know if anybody remembers the cannonball one. Didn't we do the little cannonball one there? Yeah, okay, and we had that. And I know that's a tough one to figure it out. So that's why, like I said, I you know, if you didn't see it, I guess it's okay. But I have a feeling you'll never miss it again after missing it on this one here. That's the key. Well, then the problem gets, you know, involved here, because now we got to solve for the speed at that point. So we essentially got to come back to this statement here and start doing this all again, but this time our x is known, and this time we will have some kinetic energy because we're not going to compress the spring all the way down here. So as we come back over to here, I guess it would be an mg and then 1.35 plus 0.057, and that would be my x times the sine of 40 degrees. And so that would be this first term here, saying, all right, how much potential energy change am I going to have as I go down to my point of interest, my x. And then I've got my spring here. And so we're going to compress our spring. And so this is my 1/2 times my 35 times my 0.057 meters squared. So there's the kinetic energy as we compress this. And it's not very far, so that term's not much energy. This is most of the energy here. And so then this is my coefficient of friction times mg times cosine of 40 degrees. So there's the normal force. And the distance it travels then is that far. It's the 1.35 and then roughly 6 more centimeters. So that's my force times my distance. And then of course what would be left then is my kinetic energy. And so this would be conservation of energy a second time. It's just we didn't go all the way down and come to a stop. So over here our kinetic energy was set at 0, where over here it's not at 0. So if you run through all this math, you get a kinetic energy of 2.691 joules, which then, setting that equal to 1/2 mv squared, gives me a final speed of about 3.40 meters per second. And so there's the speed there. So there's a lot of work in part B than I realized. Now I'll be quite honest with you, I think there's even an easier way to solve this one. Some of you saw it, and congratulations for that. I was kind of after the physical picture. That's how I solved it in class. I was after and said, hey, when is the speed, or excuse me, when is the acceleration going to be 0? Which is where its speed will be its maximum. And so I did it by forces. And so I did it by the physics. But another alternative is certainly to say this is equal to the kinetic energy. So there you have kinetic energy as a function of x. So just take the derivative with respect to x, set it equal to 0, and solve for x. So that would be certainly a valid way of doing it and looking at, you know, maximizing your function as opposed to looking at the physical picture of it. And and of course it works. Well, finally, then the last one here, number 5. And number 5 is that double pulley system. And so we saw it a couple times in class. And I was glad to see that most of you caught it right away. You're like, oh yeah, I saw this. I saw it twice. And one a movable pulley, one fixed pulley. Notice the 2-to-1 ratio. It is a little different than any of the setups we had. This one I tried to make it a little bit different. I tried to get one to go up and one to go down. So I guess that's not any different than the one we saw. If you remember, we had like a block A and a block B, and we had to find their speeds when they separated a distance of h. This one's on an incline, so in that sense it's different. But other than that, one goes up and one goes down. So the picture kind of looks like this. You've got the bigger block here at 10 kilograms. The cable comes around like this somehow, wrapping around a pulley here. And then this pulley is here. And the idea is if this would go down 0.2 meters, and again, I think it's in centimeters. Let's see, carefully look at the pulley system. So then it describes the pulley system. Yeah, but it says after the 10 kilogram goes down 20 centimeters. So again, watch your units. It's going to go down 0.2 meters, which then means this goes up 0.1 meters or 10 centimeters. And so this goes up at half the rate of that one. Okay? So you got to notice that 2-to-1 ratio. Otherwise you might do a poor substitution. You might say they have the same speed, which they don't. Or you might say they have the same acceleration, which some of you who are doing this with forces, you said they had the same acceleration. Some of you even said they had the same masses of the block, and I wasn't sure why you did that. I think maybe you didn't realize what you were doing when you substituted M for M. It was just kind of, you know, you got a free body diagram, it's got an M in it, you got another free body diagram that's got an M in it. I don't think you really thought they had the same masses. But it's easy to do that when you're not reading the math. And so we get back to that. Read the math. Make sure you know what each part of that equation means there. And so a lot of details, I guess, is really the short answer to this whole test. I guess you can see that. You probably saw that right away in the homework. And so I think this test is a big notch up from the last test we took. There's just so many details to keep track of. And it just grows. this next 3-4 chapters, just a lot of details to keep track of all the little pieces. All right. Well, this one I would choose to do it by energy. The clue to me would be the fact that, number one, they're asking for what is the speed. It says, what is the speed of the 5 kilogram block after the 10 kilogram block has moved 20 centimeters down? So they're asking for speed, I know distance. That's a sure clear to me to do, let's do it by energy. And I think most of you did. I didn't really keep track, but a lot of you did it by forces and did it correctly by forces, I might add, too. So you can do this one by forces. It's not as hard as stuff with a spring. When they have a spring and you try to do it by forces, it becomes really challenging because the force changes with X. At least in this one, the forces don't change, and it makes problems a little easier when you have constant forces. You just have to remember that the string wraps around and you got 2 strings essentially on here. So you got twice the tension here as there. And you got to watch your sign as it goes up and down. And you got to realize they have different accelerations. But other than those little details that you also have to keep track of when you do your energy, it pretty much falls into the same place here. But doing it in terms of energy, I would have said, all right, my initial gravitational potential energy, and there's no spring, so I shouldn't even do a spring one. My initial kinetic would equal then to my final gravitational, and then my final kinetic, and there's no heat either. So you can see that the hard part on this one really was the pulley system, the 2-to-1 ratio that we were working on in class here. And so again, kind of like that, number 2, where do you want to call y equals to 0? I think for the bigger block, I would call that y equal to 0. And for the smaller block, I would call that y equals to 0, so that as this one goes down, it goes down to 0 energy, so it has positive height. And this one, as it goes up, it has positive energy. And so if you do that, you're going to start off with this one with 0 gravitational energy, but this one having m g, and its height would be 0.2 times the sine of 30 degrees. And so there's your little picture with 30 degrees. And that's it for the energy on the beginning part of it. That's how much it starts with. And so now, as it comes down, this one goes up. So this would be 5 mg. Its distance is 0.1, and its height, again, is sine 30. So that's the gain in potential energy of the smaller block. And then they're each moving now. So it would be 1/2 of 10 times the velocity of the number 10 squared, and 1/2 times 5 times the velocity of number 5 squared. And so I put a little subscript to indicate this is the velocity of the 10 and the 5, because again, want to keep that double pulley system in my mind, that there's a 2-to-1 ratio here. And so now I can put in some numbers. Putting in these numbers, it is a 2.45 joules. Putting in this number is 9.8 joules. And then, since they ask me what is the speed of the 5, why don't I replace the speed of the 10 with the speed of the 5 and then double. And so this is the speed of the 10. The 10 is going twice as much as the 5. And so then I will have the speed of the 5 in there twice. And so then I can get the speed of the 5. And so there is the speed of the 5. How fast is it going? And so forces, energy, and then looks like another energy or force one at the very end. Kind of your decision there on which way you wanted to handle that one. Alrighty, well, like I said, I hope that went well for you. And if not, hopefully now you kind of see those missing pieces, okay? But like I said, it's a tough test. This one always is. So if you're scoring in those 70s or higher, you really did do a good job. So you don't always feel like it when you come back with a test sometimes at 71 and go, wow, okay, that's a pretty good score. But obviously 80s and in the 90s you did an exceptionally well job. Lower than that, take advantage of that extra credit one. Think it through, work on these problems. Get familiar with these types of problems, because you'll see these again on the final exam. Okay, and you'll need to make a decision. Are you going to do it by energy? Are you going to do it by forces? You know, don't forget some of these ones. And like I said, especially some of these, the plus X, just so easy to overlook that if you don't have that physical picture there. All right, well, now what? Well, let's go into chapter 9 then. So what do we have? 9, 10, 11, and 12 here. And so that's our next big unit here. And so where are we? About halfway done, hair over halfway done. Point-wise, you might want to keep in mind that depending on where you are, there's good news here. I mean, the good news is if you've done well, great, keep it up. But remember this, we haven't even done half of the points yet for the semester. So if you didn't do so well, remember this, we haven't even done half the points yet for the semester. So they're still out there, right? They're still got another test and a final exam. And those two add up to more than the first two, because the final exam is equivalent of a test and a half. So if you want to think of it as the 3 tests and the final exam, that's 4.5 tests. And you've done 2. Okay? And so there's still a lot to be done out there as we move on. Well, let's move in then to chapter 9. And also, don't forget all this conservation of energy stuff, because this conservation of energy stuff we're going to need, particularly as we get into chapters 9 and 10 and 11, and all these forces too, as we start looking at things that are more complex and start looking at all their details. So looking here at the momentum, which is what this chapter is about, but maybe I don't need to say that. I don't know if you're still on that study plan, but the study plan is read the chapter before you come to the lecture on the material. So I'm sure this weekend you were thinking about that and going, okay, I'm going to read chapter 9 before I come. And I won't ask for a show of hands, but that really is the best way. So if you've read chapter 9, great. Then you can hear about chapter 9. And like I said, then it becomes more of a learning experience than it does just copying down the notes. And so that's where I want to begin here, is then this whole idea of momentum. And in fact, it's a long chapter. I think this chapter 9 is probably the longest chapter in the book. It's got two main themes. It's hard to know if this one is longer or 10 is longer. Either way, we've got two really big chapters with a lot of information coming up here. I guess the flip side of that is 11 and 12 are pretty small. So, you know, we got two big chapters followed by two short chapters before we get near the Thanksgiving time, and that will be the third test there. But here's what chapter 9 is, and chapter 9 can really be, in my view, divided into two chapters. And so what I'm hoping to do today is the first half, which I would call the chapter 1, and then the next one we will do then on Wednesday. And it has to do with momentum, linear momentum. The same momentum that you guys saw in 102. Maybe you even remember the definition. What was the definition of momentum? And I'll just start with the symbol. Symbol for momentum is a P. We'll put a vector over it, so that's where it'll be a little different than your Physics 102. A lot of vectors, a lot of math. You probably noticed that a lot. That's why if I took you all the way back to the very first day, I would kind of say in that syllabus, you know, this class is very analytical. I haven't said it in a while, but the idea is to take your basic physics that you learned in 102 and combine it with your calculus and some other math that we're learning here along the way, and put those two together so we can do some very detailed type of problems. So our Math 150 and our Physics 102, and we're kind of merging them together here. And so this is our definition of momentum. They are vectors, so let me write them out in this way so you don't forget that as a vector, then it has an x, y, and a z component, although usually here at the beginning we don't use too much of the z components. But as you noticed here in chapter 6, it started to become very important that we visualize things in 3 dimensions. Less so in chapters 7 and 8, and even less so here as we get into 9. But coming back in 10 and somewhat 11, but mostly 12, at a very 3-dimensional view. In fact, my Physics 122 class is experiencing that big time right now. We're in magnetics, and so you guys will get your chance next fall, but you got to see these things in 3 dimensions. You got to see X, Y, and Z, and all the different pieces that are going on. And this is kind of our training ground for that. We got just a few chapters that really need some 3-dimensional motion. So, in either case, this is what that statement means. Maybe I should put here, what are the units for momentum? Well, I know it's been a while since you did 102, but hopefully you can see it from the symbols here. The mass would be in kilogram, and the velocity would be in meters per second. And so there's the units. For better or worse, we don't even give it a special name. We don't call it a Newton or a joule or a watt like any of those other great names we had after the scientists. We just leave it alone. That's what it is. I think I mentioned kind of the tradition is, you know, starting with Newton on, we give names after the great scientists working in that field. Coulomb, amp, volt, you know, watt, joule. There's Einstein. You're right. There's no units for Einstein, is there? But there's an element named after him. There's Einsteinium, so that's better still. Okay. All right. So he does, but he doesn't have any units there. Hertz, Faraday, all those come into play. Well, like I said, this one doesn't have any, but sometimes we do like to do this. And you'll see this in the lab today when we go in to measure the computer. It'll multiply top and bottom by seconds. Because if you group these together, what would that be? Yeah, kilogram meter per second squared is a Newton. So a Newton times a second is the same thing as a kilogram meter per second. So you'll see that on your computer screen today as we go and measure our momentum. Actually, our change in momentum. Well, we begin the chapter saying, well, why do we care about this new quantity, this definition called momentum, which is a product of a mass and velocity? Well, probably it's best to answer this way. Let's go to Newton's second law. Newton's second law said that the net force is equal to mass times acceleration. And what was acceleration? Well, acceleration is the derivative of the velocity. It's how did the velocity change with time. And then, if we take mass and we put it inside of the derivative, which is kind of backwards of what we often do in our math with our derivatives, we say, okay, you're going to take a derivative, pull out the constants. But let me put it back in here, because then you'll see that what I have is the two together, the mass and the velocity. And you get what we're going to hopefully see as a different way of looking at Newton's second law. And sometimes I would even say an easier or better way of looking at it, certainly a more powerful way of looking at it. And you'll see that as we get into some of the example problems here. So what we have then is the net force on something is equal to the change in momentum. And so that way you just have the two quantities, the force on one side and momentum on the other. You don't have mass and acceleration. In fact, you begin to see it here. Let me come back to here. If we went back to chapter 5 and I said, all right, I am going to apply a certain force. Let's just say it's 100 newtons. And if I apply it to one object, like a car, and I apply it to another object, say a bicycle, and let's just say they start at rest, so here's a big heavy car and I start pushing it. Doesn't the car accelerate? And here's the bike, which is much lighter. Doesn't it accelerate also? But do they have the same acceleration? No. I think you know the bike would have a greater acceleration, right? Less mass. But here's kind of a nice approach. What is this saying? This says if you apply the same force, you get the same change in momentum. And so I would come over and say, look, I apply a force on this car, I have a change in momentum. I apply a force on this bike, I have the same change in momentum. So their momentum changes the same. Personally, I like to kind of write it this way. dP equals force multiplied by time. Or taking it as an integral, then this is the change in momentum. So the change in momentum is the total of the force over time. And that's kind of our first section in this first chapter here, or chapter 9, is that, look, if you apply a force to it, and again, just comparing the bike and the car, if I apply that same force, 100 newtons, for the same amount of time, let's just say 1 second, I get the same change in momentum. So it doesn't matter if it's a bike, a car, a boat, a plane, a satellite, an asteroid, a planet. You apply that same force for the same time, you get the same change in momentum. And so sometimes that's nice to talk about the same change in momentum. Now, does that mean they have the same speed? No, they just have the same change in momentum. So coming back over here to momentum, momentum is mass times velocity. So you can imagine that the force on the bike and the force on the car, even though they had the same change in momentum, they don't have the same speed. The lighter object, the bike, has less mass, so it would have more speed. And then the bigger object, the car, which would have more mass, would have less speed. So the product of the two, the mass times the velocity, is the same. So after I push on the car and I push on the bike, I know something that's the same about them. They each have the same change in momentum. They each gain the same amount of momentum during that push. Not the same speed, because they don't have the same mass. But their mass times their velocity is the same. And so that's what's really nice about it. In fact, many of you can probably even remember from Physics 102 where we're going with this. It's called conservation of momentum, right? And so I said it back in 102 a lot, and I should say it here. I mean, here's really what we're after this semester. Newton's 3 laws of motion, the 3 conservational principles: conservation of energy, conservation of momentum, and conservation of angular momentum. So the same 3 that we saw in 102. And so if we can learn those 6 things, we can explain all motion. So we've already done Newton's 3 laws of motion, and we've already done conservation of energy. Now we're doing conservation of momentum. And soon, conservation of angular momentum. And so we'll have all those pieces, okay? And so that's the change in momentum. In fact, this is today's lab. We call this then the impulse momentum theorem. And it's simply saying here that if you apply a force for a certain amount of time, and it could be even a changing force, that'll get your change in momentum. It's kind of nice because if I draw some pictures over here, we could have something like this. We could apply, say, a force to some object. Oh, I'll pick on a baseball this time since we're right in the middle of the World Series again. Anybody seen Game 3? Oh, wow, what a slug for us. Fast that was. 16 to 7. I mean, that was just a good game to watch. I was just, wow. So I was glad I recorded that. I'm terrible. Usually I record it and then I kind of look at the score and go, is it worth watching? And I went to look at the score that night and it wasn't even over. And it was like 14 to 7 at that point. I was like, oh my goodness, I got to see what happened here. So, and then just what, 3 home runs by, who hit the home runs? Pools. Yeah. Man, 5 hits. You know, so 3 home runs would be 12, and then 2 singles, so 14. You got 14. Wow. Anyways, so the baseball's on. So yesterday I recorded it, and then I looked, and it was a pitcher's duel, so I just deleted it. I was like, you know, I just don't want to watch them play catch there all afternoon. So I didn't see yesterday's game. So, anyways, so picking on baseball here. Look at a baseball, right? And so you're looking at this baseball, and let's say we want to get this baseball to 100 miles an hour. Well, it could be the pitcher, or it could be the batter. The batter gets the ball to 100 miles an hour. Now, I guess in a real game of baseball, it's pitched in. But let's just say I kind of hold the ball out there on a tee. I could hit it, right? Or I could pick it up and throw it. Either way, it gets to not that I could throw it 100 miles an hour, but either way, it gets to about 100 miles an hour. How? And I would say the batter does something like this. No force, huge force for a short period of time. So we'll call that its impulse. A huge force in a short amount of time. Where the pitcher holds it in his hand, and he goes, all right, I'm going to give it a force, and goes through the whole windup. Throws, 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 throws. And so it's this huge, a smaller force, but for a much period of time. Would those end up with the same speed? Do you see it here? Isn't this saying the area under the curve? Isn't this an integral? It's saying add up the forces. So a huge force, and maybe I should have made the force even bigger because that doesn't quite look like the same area. Still not the same area, is it? All right, how about that? So maybe that's roughly the same area there. Okay? But the idea here is that it is the totality of the force and the, what I'll call the contact time, or the impulse of it. And so all of this is the total change. And as you'll see, there'll be a lot of times where we don't know the actual force. It could be very complicated. It could be something that looks like this. But I do know that if this is the force of a period of time, if I take all of this area, and even that negative area, and I put it all together, that is going to be the change in momentum. And so that's really today's lab. You hook up this little cart, and it's on a rubber band, and the rubber band pulls it, and the rubber band keeps changing the force. And it gets bigger and bigger and bigger, and then snaps it back. And you might even remember a lab like that. It's actually the same equipment that you did in the lab where we had that non-constant acceleration where the cart went out and the rubber band stretched and then pulled it back. We're going to do the same thing. But this time we won't be looking at accelerations and velocities like we did last time. This time we will be looking at the forces. And we will be adding up the force over a period of time. And then we'll see, did it change the momentum? And if it did, by how much? And so we'll see what happens. And so, like I said, that's today's lab, the impulse momentum theorem, to see if it works out. But more important than the impulse momentum theorem is this. Watch what happens now when two or more objects interact. Let's just say then I have cart number 1 moving along at some velocity, and it comes along and makes contact with cart number 2. And so they hit each other. Now in the picture I've just drawn, I got them going in the same direction. So cart 1 better be going faster than cart 2 if it's going to catch up to it and hit it. But they could be doing a head-on collision. Or one of them could be stationary and the other one be heading towards it. So I'm not really trying to say what direction they are as much as trying to just get that basic principle that if these two come together, if these two hit each other, I can write the change in momentum of number 1. And I can write the change in momentum of number 2. Now let me pause right there. Let's say they collide. Why don't I make it the easy case here? How about if I just say, here is cart number 2, stationary. Whoops, that's not very stationary. But here's cart number 2, stationary. Here comes cart number 1, it hits it. Did number 2 change its momentum? It did, didn't it? I mean, I'm looking at this going, okay, here is cart number 1. It has no momentum. It's not moving. And then it comes around and boom, now it is moving. So did this change momentum? Oh yeah, you bet. But what did you notice about cart number 1? Yeah, it slowed down. It changed its momentum too. And as you look at this, how would the change in each of these momentums compare? Wouldn't this be the force from number 2 on number 1? And wouldn't this be the force from number 1 on number 2? I mean, this is Newton's third law. that as it comes in, object 1 puts a force on object 2, but object 2 puts a force on object 1. How do these two forces compare? Yeah, aren't they equal in magnitude, but opposite in direction? And so if these two are equal and opposite, then what would you say here compared to there? They're equal but opposite. So what is the change of number 1 plus the change of number 2? 0. Good. And so we went through this in 102. We didn't write it out with any calculus, but hopefully you remember that hey, when you start having multiple interactions like this, when you bring two objects together, it's really nice to be talking about momentum. Because even if the objects don't have the same mass, the principle still applies. Watch. Now the example I showed you, they have the same carts, and so they pretty much have the same momentum. But if I try this, where this one's got a lot more mass than that one, this one still gained momentum, this one still lost momentum. But isn't this still the same true? And so regardless of how much mass they have, that would never came into play here. One is going to lose momentum, one is going to gain momentum. The total change will be 0. And so this basic principle here is simply referred to then as our conservation of momentum. And so conservation of momentum. One gains, one loses, total doesn't change. And that really is the whole first half of the chapter. Now, I think it's worth going through some problems then to work on this, because these can get pretty hard here, particularly when we incorporate the energy of it. And so let's see if we can look at it. Now, maybe I should even expand on this. I did this with 2 objects. What if there were 3 objects here? Yeah, now I think the equation would be a little bit longer here. It may look something like this. I may have, say, here's object 1, here's object 2, here's object 3. But as they come together, there might be an interaction. And so I'd say this is the force from number 3 on number 2. And this is the force on, well, from number 1, number 2. And so as I look at the change in momentum of number 2, it would be the force 1, 2, and force 3, 2 added together, and then dt. And so that would be the force on that one object. So again, would that one object change momentum? Yes, just like over here. Does one object change momentum? But the two together, the two is what we're going to use a word system now. And we're going to start putting things together. This object plus this object plus this object will be my system. In fact, you'll begin to see me, I'll put dotted lines around it and say, okay, here is my system. And so as I look at this, there is no other forces coming from the outside of my system. That's why this is the net force, and this is the net force. And the two together is my, total net force is 0 in the sense that one is equal to the other one. Here, I must admit, it gets a little more complicated, but it still comes out to be the same idea, that this would be the change in momentum of number 3. The change in momentum of number 3 would be the forces on number 3. And this one would have 2 forces on it. It would have the force from number 2 on number 3 and from number 1 on number 3. And so I would have something that looks like that. And so that would be the change in momentum of number 3, because two objects are interacting with it. And likewise over here, there would be the force from number 2 on number 1, and over here would be the force from number 3 on number 1. And so again, number 1 would change its momentum. And it would have these two forces. And you can imagine if I had 4 objects, it would start to get even more complicated. But I think you see it, maybe not so much with just 2 objects. That's the easy one. But once you get to 3 or 4 or 5, you begin to see that the change in momentum of number 1 plus the change in momentum of number 2 plus the change in momentum of number 3 would be what? 0. And hopefully you see why, because as you start adding them up, this right here, force 1, 2, and this force 2, 1, they're equal and opposite, Newton's third law. So that gives you a 0. This force right here, force 3, 1, and force 1, 3, when you put those together, you get 0. And when you put those together, you get 0. So by the time we add up all of our forces here, we're going to get 0. And so as long as we include everything that can interact as part of our system. And so there's that word again, our system. Our forces are inside of our system. These are internal forces. What do we notice right away about our internal forces? Internal forces are going to always add up to 0. And so you always get an equal and opposite. Here's the good news and bad news in that story. Good news. You've enjoyed for the last 8 weeks. When we took something like this pen and we tossed it across the room and we figured out that it made a parabola, what force did we think about? It was a force of gravity. Did we pay any attention to the intermolecular forces holding all of these pieces of plastic together? We didn't, did we? Why did we just forget about all those forces? Why did we ignore them? Why did we never even think about them? Because if you were to add up all the forces in here, guess what they would come out to be? 0. The only thing that affected the overall motion was what we're now going to call the external forces. And so as we begin to look at our objects in more detail, we'll draw a box around it and say, this was our system. This is what we've been doing for the last 8 weeks. We haven't used a fancy word like system and internal forces and external forces, but we've really taken advantage of the fact that this is our system. And as part of our system, all the internal forces added up to be 0. And the only thing we needed to be worried about was the external forces. We're now going to prove that here in this chapter. So good news, we didn't have to do it before. Bad news is now that we are going to do it, not only will we prove why we got away from it before, but now we can give size to our object, right? Did you notice our objects didn't have any size to them? I think you guys asked this a couple of times when the weights were going up and down. You said, well, are you measuring the height from the bottom of the weight or the top of the weight? And I gave you the short answer of, I don't care, whichever you want to do as long as you're consistent. But it was really much deeper than that. It makes no sense to talk about the top of the object or the bottom of the object yet, because we hadn't given size to our object. And now we can. And so now we're going to think about that. And we see that here, this first step on internal forces. And center of masses, which is the second half of this chapter, which you guys might remember from 102, where now if we have an object that has size, we have to look at its motion, and we have to look at its motion from its center of mass. And so that way when we toss something across the room like this, it not only goes in a parabola, only one point goes in a parabola. What's that? The center of mass. What do the other points do? they go circles around the parabola. So we're going to have to know how to do parabolas together with circles to figure out what is the motion of this cap. Because the cap's going to go like this. It's going to make circles around a parabola. And so our problems get a lot more detailed and a lot more complex. It even gets harder than that. As I spin it around, do you think all the points on here are traveling the same speed? So how do I calculate the kinetic energy of this thing? Yeah, I've got to take the velocities at different points and add them together. I probably got to do an integral over this. And we're going to learn some neat techniques here, and we'll learn things about the difference between rotational and translational motion. But hopefully you're just seeing the door open for the next 3 chapters. Center of mass, rotational kinetic energies, torques instead of forces. Okay. How do these things behave? They can do both now. They can translate and rotate. And they couldn't rotate till we gave them size. Well, I shouldn't get too far advanced down here, but I think you're kind of seeing the layout here. And all I want to do is start with is really kind of introduce you to the idea of this word system. We have a system. We'll draw a little box around it. Stuff inside of our system. Stuff outside of our system. Stuff that gives us forces on the inside we'll call internal forces. Stuff on the outside. And I haven't had any ones on the outside yet. And I don't even think we'll even get that far today. But stuff on the outside will be our external forces. And it's our external forces that are going to determine the motion of this. And I think this is that first step kind of proving that the internal ones really don't matter. I'm sure you've experienced this. You ever try to push a broken car by sitting in the driver's seat and pushing on the steering wheel? It won't go anywhere. Why not? Well, because as you're pushing forward on the steering wheel, what's your back doing? And pushing backwards on the seat. And so all you end up with is a net force of 0, and the change in momentum of your system comes out to be 0. To get the car to move, you got to get out of the car. Put your feet on the ground. So now you can apply a force on the car from something external of the car. Does that kind of make sense? All right, and so that's what you're going to see here. So change in momentum. Well, all of this is this, again, this statement. Maybe I'll write it out again here, but this is our conservation of momentum. One object will gain momentum, another one will lose momentum, a third one may also gain or lose, but the total change of all 3 of them is going to be 0. Now, a little warning here. What if there was an external force? Would this work out? And I say a warning because we didn't make a big deal out of this in Physics 102, but it really matters here. What if there had been an external force here? What if there had been some other force out here pulling on that one? When you add up all these forces, would they have come out to be 0? No. So when does the change in the momentum equal 0? When is momentum conserved? Yeah, when there's no external forces. If you have external forces, then momentum is not conserved. And that's an important difference here, because I don't think we emphasize that in 102. We just kind of throw it out there like, oh, momentum's always conserved. But is it? Do you always have conservation of momentum? No. You have conservation of momentum when you have no external forces. And so that's why we do problems like this, and we put them on a track with really good bearings. What am I trying to get rid of here? Friction, the external forces. If this had been like this, is momentum conserved? No. But when there's no friction, is momentum conserved? Yeah. And so we got to be careful on our system. So, an important step here is, what's your system? And you'll probably hear me say that a lot as we work on the problems. And as you ask me questions, I'll say, wait a minute. I see why you're struggling. What's your system? Do you have a system that doesn't have any external forces? Because you're trying to apply conservation of momentum, but at the same time you have external forces. There's your problem. Okay? And so we'll have two options about that. We either won't use conservation of momentum, or the other option is just to make our system bigger. Include that fourth object as part of your system. I'll give you an example. Look at this pin again. I hold it up here. If I was just looking at the pin, is the momentum of the pin conserved as I drop it? Didn't it go faster, 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 faster? Isn't the pin gaining momentum? So if I look at just the pin by itself, there is a change in momentum. Of course, that's because there's an external object pulling on it. What is it? The Earth. So what if I include the Earth as part of my system? What if I look at the pin and the Earth? So I've got the pin up here, and I draw a big box around the Earth also. And I let it go. Is momentum conserved there? It is, but how? Yeah, so the Earth pulls down on the pin, but the pin pulls up on the Earth. And so as I held it up here, I would say the momentum is 0. Then as I let it go, this has a downward momentum and the Earth has an upward momentum. The two add together and give me 0. And so I have conservation of momentum in that case. The warning is this. Conservation of momentum, yes, we're going to use it. Yes, powerful tool. We just got to use it correctly. Make sure there's no external forces to our system. Okay? It wasn't that way for energy. That's why I particularly like the order that this author does. Those of you guys who have 102, we did momentum first and then energy. But I like to do energy first. I like to say, look at energy, because energy is always conserved, period. Now, granted, it may change forms. It may become elastic energy, and it may go from one object to another. But it's always conserved. But for momentum, no, we got to watch out what's going on with our system. Is this a case where momentum is conserved or not? Well, like I said, this is the first half of the chapter. The details aren't that great, but solving some of the problems are. Let me do the first one here. Let's go back to this first one where they collide together here. Let's just start with a simple case where they each have the same mass and they collide together. If I were to ask you, what is the speed of the two after the collision compared to the speed of this first one before the collision, you would say half. Why? Yeah, I guess you would say, okay, let's look at the momentum before and say that has to be conserved to the momentum after. If, what system do you have? Well, if this is object 1 moving with a velocity 1 and it comes along and hits object 2, for me to apply conservation of momentum, I can't have any external forces. So what's my system? So my system has to be the two objects. So I start here with the two objects. And we're really kind of back to this situation where I can see that object 1 puts a force on object 2 and object 2 puts a force back on object 1. Okay. But that means when I go to add up the momentum before, I need both objects. So this would be mass 1 times velocity 1 plus, I'll just put a 0 there because I want you to realize I am adding up the momentum of my system. This happens to be the second one. It's not moving. But it could have been different. Let me set up a second part of this problem. It could have been something like this. It could have been this one already moving, like this, and this one comes up behind it. Whoops. Didn't want it to do that. But here it's already moving, and this comes behind it. And they collide. Right? And if that's the case, then when I write down what is my momentum before, I would have the mass of 1 times the velocity of 1 and the mass of 2 times the velocity of 2, right? And so that would be before. And so you begin to see there's probably thousands of different combinations I can do. One going to the left, one going to the right. You know, both going to the left, both going to the right. I could have 3 objects, I could have 4 objects. But what I need to do is add up what is the momentum before. Now in both of these cases they stuck together. So I would write it as then an m1 plus an m2 times some final speed. Same thing here, they stuck together. So I would write this as an m1 plus an m2 times some final speed. And say, okay, that is my new momentum. And so I'll finish the problem, I guess, by saying the final speed would be an m1 v1 over m1 plus m2. And you guys said it correctly when you said, well, if these have the same masses, then what you're going to get is a half of v1 is your final speed. Sure. And so this is the case where they stick together. Same thing here. If they stuck together here, although this would be a harder problem because I would need to know what is speed 1 and what is speed 2. But if they were the same masses, which they are in this case, I would have something that looks like this. And so there's kind of the setup. What is the momentums here? Well, we do, I guess, give a fancy name for all this. When 2 objects stick together, we actually call this then a perfectly inelastic. So maybe I'll just set this up here and say, okay, this is a perfectly inelastic collision. What kind of collision do I have? So be careful when you read the text, because that's easy to overlook. It'll give a problem and say, okay, 2 objects come together and they have a perfectly inelastic collision. What are they telling you there? Yeah, they're stick together. And so there is them sticking together. In fact, more general than this, what if they don't stick together? How would this change? What if I had something that looked like this? Well, they don't stick. Or what if I had something that was already moving and it comes up behind it? Or what if I had one that had more mass than the other one? And say it was already moving and this snuck up behind it. Or maybe it was coming towards it and this one came towards it like that. And they bounce off. I mean, how would I do that one? Okay, good. The only difference is there's no same velocity. But what I do want you to see, and maybe I'll draw a picture here, is couldn't we still say that the force on number 1 is equal to the force on number 2? And as a consequence of that, what would you say about the momentum? Yeah, it's conserved. It doesn't change. So maybe I'll write it this way. Here's mass number 1, moving with some velocity v number 1. It comes along to number 2 with some velocity number 2. And then they collide. And when they collide, then I'm going to have some object number 1 with some velocity number 1 final. Oh, and maybe I better put an initial here. An initial, and then final, and then final. But in order to do conservation of momentum, I have to have a system. I have to take this and say, all right, object 1 puts a force on object 2. But if we apply this general idea here, then what I would have is the momentum before is equal to the momentum after. And so I get M1 V1 initial plus M2 V2 initial has to equal M1 V1 final and M2 V2 final. And so, as you guys correctly predicted, this hopefully doesn't look too much harder. Except, did you catch that if you're going to apply conservation of momentum, your system has to have no external forces. And as simple as that sounds, I would say that's probably the most common mistake I see when students are doing the homework and doing the test. They just didn't do the conservation of momentum right. They weren't careful about what their system was. Okay? I'll even go one better. I wonder how many different problems I can set up like this. Could I have objects going to the left, objects going to the right? Couldn't I have like 2 objects, 3 objects, 4 objects? And I guess what I'm getting at is the same thing I've been trying to get all semester long. There is no way that I could do every example problem that is possible here. But do you see there's probably tens of thousands, maybe hundreds of thousands of different problems? Could you do them? You would just have to write out the momentums, right? Stand back and say, okay, what is my momentum before? What is my momentum after? Now, I'll give you a little help here, though. This is probably the easiest one, the perfectly inelastic collision. What was so nice about this one compared to this one? What do you see different? Yeah, how many unknowns do you have here? There's just one. Now, maybe I should make it clear. Usually when we do a problem, it starts off like this. You're given the masses. You are given the initial speed. Question, what is the final speed? And if that's the case, you can see that here's my initial conditions. The only thing I don't know is final speed. Same thing here. I'm given my initial conditions. What is my final speed? So one equation, one unknown. That would be easy, right? Don't expect too many like that. That's a Physics 102 type of problem. Maybe now you can see the challenge. How many unknowns I have here? Yeah, it depends on what you're given. Good point. But again, typically, the problem starts off with, this is the mass and the initial velocity. This is the mass and the initial velocity. So if you know the masses and you know the initial velocities, you have 2 unknowns, right? So wouldn't you need another piece of information here? Yeah. Any guesses what the other part of the information might be? Initial kinetic energy equals final kinetic energy plus any heat that's created when they hit. Now let me put a box around that. What am I saying here? What's that? Yeah, that's our conservation of energy. Good, right? That's back to the last 2 chapters here. What you're saying here is now when these things come together, you have this piece of information and you have this piece of information. And this piece of information, I guess, would look something like this. It would be 1/2 m1 v1 initial squared, and then 1/2 m2 v2 initial squared must equal to 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared plus any heat that's created in the impact. And so that's my second piece of information, which unfortunately could be good or could not be good, because now how many unknowns do I have? And I'll say it. Of course, it depends what your initial conditions are. But I'm going to say that the information given to you is velocities and masses. So when I look at this, I've got 2 unknowns. How many do I have in here? 1, 2, 3, right? So I have a total of 3 unknowns, but only 2 equations. So I must admit, if this is all they gave me, they better give me some more than just that. Well, let me throw a word out here. It kind of showed up earlier on. Inelastic. What does this word elastic mean? Yeah, no heat. Q equals 0. Or I heard somebody else say it. Kinetic energy is conserved. So don't be surprised if this happens. If it is not the simplest one, and this is the simple one I gave you, where it says, okay, they come in together and the velocity is, they're hooked together. That one's the easy case. Notice then it says inelastic. Now I'm trying to tell you what the word elastic means. So if the word elastic means no heat is created, what are we saying here about an inelastic collision? Right, heat. So again, as you're doing the problems and you're reading along, watch the words carefully. If they say this is an elastic collision, what have they just told you? Q is 0, right? If they tell you it is inelastic, what have they told you? They tell you there is some heat, which is usually a harder problem because that's another unknown here. However, if they tell you it is completely inelastic, what are they telling you there? They stuck together. Okay? Now we're not saying it all turns into heat, but we are saying that it sticks together. And in fact, we'll run out of time here in a few minutes, but we'll go through a little proof that will show that when 2 objects stick together, that's the most loss of kinetic energy you can have, the most heat created, hence the word perfect. But it doesn't mean all of it. That's why I want to make sure. It doesn't mean all of it, because you still have to be moving if there is some net momentum here. So it's, to conserve momentum. And that's what I want to emphasize. Is momentum conserved in the inelastic or the elastic collision? It's both. Did you catch that? I'm going to say it again. Is momentum conserved in the elastic or the inelastic? It's both. The elastic and the inelastic have nothing to do with conservation of momentum. We started this discussion a half hour ago right here. Momentum is conserved as long as we have no external forces. So whether we have 2 objects or 3 objects or 4 objects, momentum is conserved. Now, sometimes there's an interaction where heat is created, and sometimes there are interactions where no heat is created. And if no heat is created, we call it elastic. If heat is created, we call it the inelastic. But be careful with that word. It has nothing to do with momentum. So remember that. 2 things collide together, you know momentum is conserved. You guys who had me for 102, you probably remember me saying that. I'm going to say it again. You're doing a test question, particularly, obviously at the end of this chapter, but when it comes to a test question with a lot of other problems, you're like, okay, which principle do I use? Do I use forces? Do I use energy? Do I do momentum? And here's your key about momentum. They collide. What do you know about the momentum before and after? It's conserved as long as that's part of your system, the 2 objects. Does it matter if some heat is created or not? No. That has nothing to do with it. So this problem actually can be solved if I told you these 3 things. are really two things. I have a collision where they don't stick together, and the collision is elastic. Do you see that? Because once I said I had a collision, you know this is true. And then once I tell you it's elastic, then you know this equals this, and what's Q? 0. So how many unknowns do you have? 2. How many equations do you have? 2. 2 equations, 2 unknowns. Can you solve it? Warning. Squares. Linear. Can you solve it? You can solve it. Easily solved? Perhaps not. Maybe a page of algebra. Maybe a half a page if you're really efficient with it. Okay? But the setup is really what I'm after. We're going to run out of time here in a few minutes. I won't actually solve it. And probably it's best I don't. I just want you to see this. Momentum is conserved. Energy is conserved. And in the case of elastic, that's 0. 2 equations, 2 unknowns. I can solve it.
Does Q still involve friction?
Oh, the question is, if you didn't hear it, does Q involve friction? Yes and no. Depends which friction you're talking about. Let me come back over to here. All right? So here's my interaction. They come along, and they do this. Now, in this case, I'm saying that there's no friction on the track. If there was friction, could I even use conservation of momentum? No, because then I would have an external force. To use my conservation of momentum, I have to have no friction down here against the table. Now, with that said, then where does the heat come from? Yeah, let me turn it around and give you a collision that is elastic. The heat comes when those molecules hit these molecules. So there's no friction here. There's no heat with these molecules, but there is friction here. So that's subtlety. All right, well, I guess we'll have to stop there for the day and come back on Wednesday and off to